Can I ask you guys to stand mostly to the right of the table? So whoever's presenting go left and then.
Hi, I'm Dawn.
Sebastian. Sam.
And our project is on the pseudotemporal analysis of gene regulatory networks in neurodegenerative. So the motivation for this project is that GRNs in neurodegenerative diseases are incredibly complex and understudied. So if we are able to find the gene interactions there, there would be a lot of very serious clinical implications that we could follow from that. And moreover, a lot of the current analysis that has been done has been focused on bulk RNA sequencing data. However, the drawback here is that regulatory networks are often cell type specific, so we would have a lot of advantage in using single cell RNA sequencing data to do that. The disadvantage of single cell RNA-seq is that it captures the data at a singular time point while it is individual cell specific. But we want to be able to model these dynamics over time because that's how gene regulation works. So an overall pipeline of how we're going to accomplish this is that we're going to start with an input of single cell RNA-seq data as well as cell type marker genes. And we're going to take this to figure out what cell type specifically we want to analyze. From there, we want to use disease state enrichment so we can figure out a way to cluster cells that are within the same disease state. Now, this is somewhat vague and we'll go into it later, so don't worry about that. And then from that part, we'll select which genes are most important for the disease states of the cell type that we're looking at. So at this point, we'll have essentially cells that are in disease state 1 and so forth until whatever the end of the disease you define is. And using that knowledge, we want to essentially simulate cells that are in the first disease state and the second disease state and so forth. And using these simulated cells form a dynamic Bayesian network that allows us to see gene interactions over time.
So we'll run through some of our methods and then get to the results. First, we had to do a cell type annotation, like Donna mentioned, that a lot of these regulatory networks are cell type specific. So we used multi-resolution deconvolution to separate out the single cells and then annotate them using markers for different cell types. And then when we use this method, it's a tool called ExtraNet, we essentially get a number of cell states. And we can correlate those cell states with different biological pathways. And that's what this middle figure here is each column is a different cell state. And then the value of the cell is the enrichment for that cell state for the pathway. So you can see there that the fifth cell state over has very strong enrichment for disease association, which suggests that the pattern of gene expression for cells in that state is similar to a pattern of gene expression that you would expect for cells that are associated with disease. And this is an approach we use later, actually identifying the disease progression state of the cells within the cell type. But we also thought it was interesting to look at this for all the cell types, which motivated the cell type that we focused on, which, as you can see, is the microglia. So in the top right there, that's kind of the same layout as this figure off to the left, but with the transparency attribute set to the enrichment for this fifth cell state. And you can see that most of the cells that are in that disease state are microglia. But what kind of validates this kind of multi-temporal approach, if you look in the bottom right there, there is a gradient for the enrichment of that state. So some microglial cells do exhibit this disease-associated pattern, and some don't. So that was what motivated us to look through this microglia. Then, using a similar approach, we reran the multi-resolution deconvolution and found four core states. And then we did the same correlation for disease. And here you can see that both the first and third cell states have a pretty strong disease association. The first had the strongest, but you could kind of make an argument for either of those cell states. So we also looked at the Braak stage, and you can see here that there's kind of this progression. Braak stage is a measure of kind of the progression of Alzheimer's disease. And you can see stronger enrichment in later Braak stages. So ultimately, we look at this first cell state to kind of define our disease score for an individual cell, which is the enrichment for this state. And then just kind of as we were exploring our data, we also looked at the enrichment for these different cell states for different geo terms. And we found that the first cell state was highly enriched for GTPase activity regulation. And I thought kind of particularly interesting to note that fourth cell state there, which is kind of reversed in the Braak stage, so less enrichment in later stages, has strong enrichment for T cell activation and immune pathways, which kind of indicates that maybe there is stronger immune response at the earlier stages. So having identified this first cell state as kind of our disease-associated state, we were able to assign kind of a score, what we call the disease score for each individual cell. And that's what this middle figure here is. This is the same gradient that you saw earlier when you were looking at all the cell types. And we were able to use that score to kind of bin the cells, and that's what the final clustering is on the right figure. We used a couple different approaches to try to cluster these cells. On the left, these are ActionNet has a function which can actually assign cells to a state. So that was what this clustering here was. And this approach kind of ordered the cells, but there were some contradictions in what we looked at. For when you actually looked at the shape and the layout of the cells, there wasn't a clear ordering from these cell states. So we ultimately used this disease score to cluster and order our cells. Finally, before we trained our network, we first tried training the network on the genes which defined that disease state, the genes which were differentially expressed that define that state. But we kind of ended up with a lot of noise there. So what we did here, and what the figure on the right is, well, I'm sorry, first we took our entire library, 17,000 genes, and filtered down to those in the KEGG pathway for either Alzheimer's or Huntington's, which gave us 139 genes. And then we plotted the average expression of those genes across our 4 time points. And you can see that some genes are highly variable across the time points, and some genes, these are just the top 30 here. There's basically an entire noise floor below this, where the rest of the 139 genes don't show any variation across the time points. So we used this clustering of the rows to further refine the genes that we looked at, both to reduce noise and limit the computational complexity. So we weren't trying to learn a network with 17,000 times 4 nodes.
Yeah, so a key portion of this project was being able to actually impute the data so we can train a network on it. So now that we essentially have 4 clusters of cells that we defined, or any n number of clusters, what we do is we use a various number of approaches to essentially learn the gene expression levels for cells of that disease state and simulate cells based on that, so that essentially we can train our dynamic Bayesian network across this entire matrix instead of having this kind of sparse matrix where you only have a certain number of cells that are uncorrelated between each disease state. And in order to do this, the best approach we've used so far is using like a static Bayesian network to essentially learn the interactions between gene levels within the same state and simulate based on that. So then now we have this complete matrix that we can use saying, okay, a simulated cell has this gene expression level when it's in disease stage 1, which progresses to this and this and this and so forth. So then we can actually use a dynamic Bayesian network approach to learn and see how the genes are being up and down regulated throughout the progression of the disease. So the best algorithms that we were able to find were the constraint-based algorithms. And these essentially take a two-part process in which the first step is basically using confidence tests to figure out if there's conditional independence between 2 genes. And there's a variety of different methods that we use essentially from the BN-Learn package in R. And we decided which methods were best based on which ones showed the most consistency in the edges that they were able to find. And most of the constraint-based, so the last 2 there, hill climbing and taboo search, are score-based learning algorithms, which showed very poor performance, versus essentially all of the constraint-based algorithms showed similar performance between around like 8 to 12% consistency of edges. So we use those. And once the basic structure of the network is found, you can find the distribution of the gene expression levels at each node based on that structure. So here on the bottom right, you see like these are your genes at the top level is your genes at essentially disease stage 1. And this is how it's progressing across the various stages of the disease.
So for the sake of time, I'll push through this a little bit so that Sebastian can get to talk about some of the analysis we did on Huntington's data. But we plotted our networks as an adjacency matrix, which is a little bit more interpretable than this. And I just want to highlight a couple of things. We looked at first the nodes which had the most children, so which other expression levels were most dependent on. And we found a number of genes which are well supported in the literature to have a strong effect on Alzheimer's disease. APOE, APP, and EFDH significantly are the ones highlighted here. One kind of confounding factor with this is that almost all of our highest degree nodes were in this first time point, which makes sense because edges can only go forward. So you're a lot less likely to have high degree nodes in your third time point than in the fourth one. So we also looked at centrality, and we still found genes which were central in the network, which had support within the literature. There's a couple highlighted here. We looked at two different forms of centrality. The one I specifically want to highlight here is PLCB4, because we were only able to find kind of limited support in the literature for it. I found one paper which suggested PLCB4 is part of the phospholipase signaling pathway. And there was one paper which said that they found an indication in several brain disorders, but there's not a ton of literature out there. But it showed up not only as one of our most central genes in terms of doing this, but also as one of our highest degree genes, not in the first time point. So I think it'd be interesting to do further study into this.
Something that was interesting also in those is that a lot of these genes that came up with a lot of children were mitochondrial electron transport chain genes, which is not something that has been really discussed much in the literature, but is consistent with unpublished data. And it comes up again here. So in order to dissect the mechanism in a more pathway-specific manner, we did is we reran this, a variation of this on a well-characterized cell type in an HD data set, where instead of clustering by using the entire transcriptome, as we did for the AD data, which is the figure on the left side, I'm sorry, the top, we clustered again we did actional clustering using only genes in a specific pathway. In this case, we chose the KEG-HD pathway. And that results in if you project disease marker genes here, you would see a gradient more or less across the lower figure that you would see at the top. And when we do clustering, in this case we did Duchamines, we actually used LIDAR, which clusters based on connectedness. You see a more linear relationship in terms of disease progression. And then we did the exact same type of network analysis we did for AD, and we found is 4 disease states, where states that are in 4 were more associated with disease. State 4 particularly recapitulates a lot of what has been seen in the literature with regards to mitochondrial RNA expression in HD. And once again, in our adjacency matrix, we saw that the nodes associated, or the nodes that had the most children, were also on electron transport chain, mainly complex 2 and 3 genes. And with that, we would like to thank Shaheen and Carlos for mentoring and supervising.
So, can you go back to your summary slide, basically, or I guess you can do that one. Two quick comments. So the first one is you assume a linear path to disease. Suppose that microglia could go either to disease state 1 or to disease state 2. And sort of any kind of pseudotime between them would be confusing how far along you're going. I guess by selecting first a cell type and then selecting only one cell state, you're kind of hoping for a linear path. But I'm just curious if you had multiple, in your model, multiple disease states, and then the path to those states, and then you could sort of somehow subdivide all these different paths, whether that would be more likely to capture the diversity of disease.
So if you're able to actually cluster this cells differently and you can do the pathway, the Imputation network definitely is able to support divergence in the network. Essentially, the approach is just in a turn blacklist any edges that would be going reverse in the direction of disease. So if you know that it's going here and here, you can just say, okay, those are the only edges we're going to allow on this graph, and that's perfectly supported.
Yeah. The other question is related. I mean, yeah, you only show changes in microglia, but I'm just curious if you exclude microglia and if you now focus on each of the cell types in your Lyra analysis, whether you will also find one or more disease paths down additional cell types.
Almost certainly, yeah.
Okay.
We chose the one that was most enriched for the disease state because the simplicity
Sure,
and
of course.
validation.
Yeah, we also looked at oligos, and there was some signal, but I think the data was a little bit noisy in our cell.
But it may have been noisy when you're looking at all the stuff together, maybe
So we specifically looked at oligos. I think there was an issue a little bit in our cell type like annotation. Essentially, when you look at the microglia, we had this. Where to go? Oh, we're back
Yeah,
in
yeah.
our presentation. Here, so there was kind of a nice spread of disease enrichment for the different cells. The oligos kind of had a little cluster here that lit up like a Christmas tree and everything else was dark. So these were probably just misclassified.
I see.
And so just for the sake of
Yeah.
moving forward, we want to.
Cool. Other questions?
What was your method for doing stuff like annotation? Like, I'm just interested in how you guys did it.
Yeah.
So I don't think it was part of their project, someone else.
Oh, was it already been?
It uses PageRank to rank the genes and give it a list of genes, and then it generates a column score. For a cluster, yeah.
Okay, great. Can you fast forward to the next?